Kubernetes, a backend of the internet. A lot of tech companies are currently implementing it, so right now it's an extremely valuable skill to have. How does it work? Well, that's what this video is for. You should gain a solid base of this technology after you watch the whole video. I'm also making this so I can rewatch it every time I need my memory refreshed. By the way, if you don't know what containerization and Docker is, I'll link it somewhere on top and on the description as well, because Kubernetes is built on top of containerization and Docker, so it's absolutely necessary that you understand those principles before you jump into container orchestration systems like Kubernetes. Let's start with a very quick demo. First, you want to make sure that Kubernetes is installed and running, and you can do it in the app with this option, enable Kubernetes. Anyway, once it's enabled, actually you can check if it's enabled. Just open a command line, and you can make sure that Kubernetes is working fine by typing kubectl version in a terminal, and you see that it's running fine. Now let's create the same deployment we did last time. And this should do the trick, and you see it started already. And now they're running. By the way, this is the Docker app, and here I have my pod running, and this is the Kubernetes dashboard, which we'll install a bit later. And now that we have a deployment running, we have to actually expose it to be able to access it. So that's done with kubectl expose. And now we have the service exposed. So if we curl it, or if we access that place, as you can see, just like last time, it's running fine. And now to delete them, and this should do it. And so now you see both of them are deleted. And here, yep, gone as well. Alright, so I'll go over this demo with more detail after explaining some core concepts. So you should already know what Docker and containerization is. We saw the quick demo, and now we'll see what Kubernetes is, as well as some core concepts such as components, objects, and pods. We'll walk through the basics, see the demo in more detail, as well as see some stateless and stateful examples. Kubernetes is sort of the backend of the internet. The name Kubernetes originates from Greek meaning helmsman or pilot. Kubernetes is an open source container orchestration engine for automating deployment, scaling, and management of containerized applications. Kubernetes coordinates a highly available cluster of computers that are connected to work as a single unit. So here are some of the features of Kubernetes: automated rollouts and rollbacks, service discovery and load balancing, storage orchestration, whether it's local storage or cloud storage, secret and configuration management. This is to say that there are adequate ways to store sensitive information. Automatic bin packaging, so you provide Kubernetes with a cluster of machines that it can use to provide containerized tasks. Kubernetes makes the best use of your resources such as CPU and RAM. Batch execution, horizontal scaling, self-healing. Kubernetes can restart, kill, or replace containers that dissatisfy your desired state. And it's designed for extensibility. When you deploy Kubernetes, you get a cluster, and we see a bunch of different things. Two main things: the control plane, which is the blue rectangle, as well as nodes. First, the nodes. Nodes are worker machines such as your computer or servers. They are the ones that run containers. Every cluster must have at least one worker node. Worker nodes host the pods. Also, normally would have multiple nodes to provide fault tolerance and high availability. So each node has a kubelet and kubeproxy, and we will zoom in on the nodes in the next slide. But first, let's check the control plane. The control plane manages the worker nodes and the pods. The control plane usually runs across multiple computers. The API server is the front end of your Kubernetes control plane. It can scale horizontally, meaning it can spawn more instances of itself. etcd is a consistent and highly available key value store for Kubernetes cluster data. The scheduler is a component that watches for newly created pods and selects a node for them to run on. C-M stands for controller manager. The controller manager is actually multiple processes bundled for simplicity. You have node controllers for bringing nodes back up, job controllers for one-off tasks, and more. The C-M is actually the cloud controller manager, which is quite similar to the controller manager. The cloud controller manager is only present if you are using a cloud provider. This component embeds cloud-specific logic and APIs. Apart from that, it's quite similar to the controller manager. It has node controllers for syncing your provider's state with the cluster state. It has route controllers for setting up routes in the underlying cloud infrastructure. service controllers for managing your cloud provider load balancers. So now we have an understanding of all these components, so let's dive deeper. Here we can see a worker node in more detail. The worker nodes host the pods. They maintain pods and provide Kubernetes runtime environment. The kubelet is an agent that runs on each node in the cluster. It makes sure that containers are running in a pod. Kubelets can manage a set of pod specs, so multiple pods. Kubeproxy is a network proxy that runs on each node. It maintains network rules on nodes, allowing communication to the pods from inside or outside the cluster. Docker is the container runtime. It's responsible for running containers. Kubernetes pods, the smallest deployable units of computing in Kubernetes. They can have a group of one or more containers. They are a logical host. You can compare running multiple containers inside a pod, like running multiple apps in your PC. They share storage, networking, and contexts. They are co-located or scheduled, which means that the scheduler will assign the same node for them. On the picture, you can see multiple pod examples. You have a container on the first one, a container and a volume on the second one, two containers and one volume. Each pod is assigned a unique IP address for each address family. Every container in the pod shares the network namespace, including the IP address and the network ports. So inside a port, the containers that belong to the port can communicate with one another using localhost. When containers in a pod communicate with entities outside the pod, they must coordinate how they use shared network resources such as ports. Containers in different pods cannot communicate by default. Pods on a node can communicate with all pods on all nodes without NIT. Agents on a node, such as system daemons or kubelets, can communicate with all pods on that node. So we talked about the Kubernetes components. Now let's talk about the Kubernetes objects. And they sound pretty similar, right? Kubernetes components, Kubernetes objects. Anyway, Kubernetes objects, they are persistent entities in the Kubernetes system used to represent the state of your cluster. Kubernetes objects are basically YAML files that Kubernetes stores in a master wants this object in this state drawer. Think of them as a record of intent or desired state. They describe what containerized applications are running and on which nodes, the resources available to those applications, the policies around which those applications behave, such as restart policies, upgrades, and fault tolerance. So objects have object.spec. Object.spec is the desired state. You set it at creation. Object.status is the current state. Kubernetes updates it. So here's a very common object, the Kubernetes deployment object. This Kubernetes object represents an app running in your cluster. Kubernetes will try to satisfy this object's desired state at all times. And as you can see in the scheme, the deployment object is actually stored in the control plane in the etcd. This way, if something happens to a worker node, another one can take its place, just like in real life. Next, to update the deployment, you must update the deployment object. You can edit the objects in many ways, after which your desired state changes, and Kubernetes will start rolling the changes automatically. So here's a deployment example. It's basically a YAML file. You see its kind is a deployment object. You can see its name, it's nginx deployment, and in the specification, which is the desired state, you see that it has 3 replicas. Its selector is app nginx, and then we have the template. So it's running one nginx container from the Docker Hub image, and it's listening to port 80. So this YAML file can be applied with the first command line, kubectl apply -f, which stands for file, and then you specify the YAML file. And once you enter that command, Kubernetes will basically create this desired state. And then you can check if they're running with kubectl get deployments and get pods, and you'll see that they're running very fast. And now for the second most common object, a service. The Kubernetes service is an object that defines a logical set of pods and a policy by which to access them. Services allow selected apps to receive traffic. This is very necessary because the cluster is a dynamic environment where nodes can go on and off, and you need a way to reliably communicate with the containers. So on the scheme, you can see that the service basically targets specific pods even if they have different IP addresses. So you can use that service to communicate with apps even if they have a ton of replicas. There are 4 different types of services. The cluster IP, which is the default, it exposes the service on a cluster internal IP, making it reachable only from within the cluster. The node port exposes the service on each node's IP at a static port. This grants access from outside the cluster by requesting the node IP, 2 points, node port. The load balancer type exposes the service externally using a cloud provider's load balancer. The external name maps the service to the contents of the external name by returning a CNAME record with its value. So here we have an example of a service, or SVC. So here the selector of that service is app A. So it will target any pod that has the app A label, regardless of the IP. Here's the YAML example. So the kind is a service object, the name my service. Then in the spec you see that the selector is app my app. So the service will target any pod that has the app my app label. Now let's quickly install the dashboard, which is quite good to have. So this is the Kubernetes dashboard where you can see your deployments, your pods, your everything basically. And you can also manage them like this. So you see the YAML and the JSON format, and you can update it. So I'll actually link this bit in the description of the video as well. So you can just copy paste. So basically you will have to first open a terminal and then paste this command. And then you go here in this GitHub page. So in the GitHub page, you want to basically copy this bit and save it as a YAML file. And also copy this bit and save it as a YAML file. After you've created the two YAML files and copied the right code in it, you save them. And then you can just kubectl apply-f both files. And after you've applied both files, you basically have to open a new terminal and type in kubectl proxy. And it will basically launch your dashboard. And after your proxy, you basically have to open a new terminal and copy in this bit, and this bit will give you a token. And you copy that token, and then you go to this address, and finally you paste your token, and that will finally give you access to your dashboard. So a few more things. If you're running on multiple environments such as cloud and local, you want to make sure that you're working on the right context. And you can do that with kubectl config current context. And you can change your context with kubectl config use context and my cluster name. Alright, next let's look at some basic commands. So here you can see a lot of commands. I'm not going to go over all of them, but if you're working very closely with Kubernetes, you will probably know how to use most of them. And I'll link this in the description as well. Let's go over the most important parts and very quickly. Check your config with kubectl config view. Create objects with apply-f in your YAML file. Use the command get to find your objects. Get services, get pods, get deployments. Use the command describe to see more information about your objects, such as nodes, pods. Update your objects with set image. Create rollouts, undo rollouts. Create services with kubectl expose. Scale your resources with kubectl scale. Specify the replicas. Delete your resources with kubectl delete. You can delete pods, services, and everything. Interact with your pods with kubectl logs. Run an interactive pod. Execute the command inside the running pod. Execute an interactive terminal inside the running pod. Get your logs for objects. You have Corton to mark a node as unschedulable. You have Drain to prepare your node for maintenance. Tap node to show metrics for a given node. Alright, now let's see a stateless example. Here we'll have one Redis backend with one leader and two followers, plus two services, one service for the leader and one service for the follower. And then we'll have a PHP frontend with 3 replicas and a service which will be a load balancer. So here's the scheme that I just drew to show you how the components interact with one another. As you can see, the traffic comes from here into the frontend load balancer service in the port 80, which is the default port. And then it goes to the frontend deployment, which has 3 replicas and has the container port at 80. So normally you could have one backend database, but here to have more availability, we can create a Redis leader and 2 Redis followers, which are both backend deployments, and both of them need a service in order to be able to communicate with the front end. And here, in order to improve the availability, what we're doing is basically making sure that the front end writes to the Redis leader and reads from the Redis followers. So overall, this is one of the classic structures you will find, and one of the easiest ones. So this is one of the official examples. It's deploying a PHP guestbook application with Redis. The first thing is we'll create a YAML file with the backend information. So this is a deployment object. Its name is Redis leader. It's got 1 replica. It has 1 image, and this is the URL of the image. It has some resource request values, and it has a container port in 6379. Now we can apply this file with kubectl apply-f and link that file to it. And then if we do kubectl get pods, we will have the backend running. And now we want to create a service for that backend. So we create a service object. And we give this service a selector identical to the previous backend deployments labels. So this bit. And once we have our YAML file set, we can apply it with apply-f and that file. And if we get services, we see that the Redis leader service is running. And we see that the service type is cluster IP because we don't need an external IP because we won't be accessing the backend from outside the cluster. And next, to make the backend highly available, we're going to add a Redis followers to the backend. So here we have another deployment, and it's another backend, but it has a different role. It has 2 replicas, and it has a different image. And then we can also apply that file with apply_f. And now if we check our pods, we have 2 followers and 1 leader. All of them are the backend Redis. Now we also have to create a service object for the 2 follower backends. And basically it's the same thing as before, except that the role is different. This time we want to target the followers. And apply that as well. And now if we get the services, we have the follower service and the leader service. So we have a good backend, and now we need the front end. So for the front end, we want to create a front end deployment YAML. So it's a deployment object. It has 3 replicas. It has the following labels. So its label is app guestbook and tier front end. It has 1 image fetched from this URL, and it's called PHP Redis. It's setting some environment variables and some resource requests, as well as a container port. We also apply this file, and now the final step, allowing access from outside the cluster into the front ends. So for that, of course, a service. So we create a front end service object. The selector is the same as the front end's label, and in the spec, you would normally put in type load balancer so that the outside world can access your front ends. So with this service, you're allowing access from outside into the port 80 of your guestbook front end. And of course, you apply the file. And if we get service, you have the front end, as well as the Redis follower and the Redis leader. Next, if you have too much traffic and you want to scale, you basically go kubectl scaled deployment front end, and then you specify the replicas you want. All right, just very quickly, I want to talk about volumes. So a volume is a directory accessible to the containers in a pod. So 2 things, persistent volumes and persistent volume claims are independent from the pod lifecycles and preserve data through restarting, rescheduling, and even deleting pods. So persistent volumes are a piece of storage like a node in the cluster that has been provisioned by an administrator or dynamically provisioned using storage classes. Many cluster environments have a default storage class installed. When a storage class is not specified in a persistent volume claim, the cluster's default storage class is used instead. When a persistent volume claim is created, the persistent volume is dynamically provisioned based on the storage class configuration. The other thing is persistent volume claims. This is a request for storage by a user. It's similar to a pod. Pods consume node resources, and persistent volume claims consume persistent volume resources. Pods can request specific levels of resources, such as CPU and memory. Claims can request specific size and access models. So basically, when your app needs a persistent volume in its application, it will fire up a persistent volume claim and claim a bit of volume that is persistent. Alright, with this information, we can go to the next slide. And now let's see how to implement a stateful example. Stateful meaning that the app preserves state or data after reboots. I usually prefer stateless over stateful, but both have real-world use. This is an example on how to implement WordPress within Kubernetes. So here we'll have a backend, which will be a MySQL database, plus a service for it, and the front end will of course be a WordPress instance with a load balancer to serve traffic to that instance. So here we use persistent volumes and persistent volume claims for both the front end and the back end. On the back end we have a MySQL database, so obviously it needs persistence. On the front end we have a WordPress instance which needs persistence in order to store things like blog posts. Also for information, in local test clusters the default storage class is host path, so the files are saved in a temporary folder. So this is also a quick scheme that I've made to help you understand all the components and their interaction. So let's go from the beginning. Here we have the internet on the bottom. So the machines on the internet will interact with the front-end load balancer service on port 80. And that front-end load balancer service is communicating with the front-end instance, which is a WordPress instance deployment object on port 80. The WordPress deployment object has a persistent volume claim, and it's mounting it at var www HTML. And because WordPress instances require the database password, it can get that password from the secret object. So the frontend instance is also communicating with the service cluster IP, which is the service object for the MySQL deployment object. And that MySQL database object is also using a persistent volume claim. So to summarize, we have two deployment objects, the WordPress frontend instance and the MySQL backend database instance. And both of them have persistence volumes, MySQL PB claim and WordPress PB claim. And also both of them use the secret object in order to recuperate the MySQL database password. And finally, both of them have services, and the backend has a cluster IP service and the frontend has a load balancer service because it needs access from the internet. So now that we understand the structure, let's see how it's coded in a use case. A secret is an object that stores a piece of sensitive data, such as a password or a key. So to create the secret, you can use a customization.yaml, and inside it, you can just write this secret generator with the name MySQL pass and the literals, which is password equals your password. So here we have a MySQL deployment YAML file, and it has three different things. First of all, a deployment with a MySQL image. Second thing is a service, and it selects the WordPress MySQL database on port 3306, and it's a default service type. And the new thing here is the persistent volume claim. So the PVC has an access mode, and here it's read write once. It also has a resource request of 20 gigs of storage. And then let's check the deployment. So its name is WordPress MySQL with the app WordPress label, and it has quite a big specification. So as in the previous cases, we see the containers, but this time we also have volumes. So this is kind of similar to Docker volumes, but also a little bit different. So in volumes, we have the volume name as well as the PVC, and the claim name is MySQL PV claim. And if we check here, the persistent volume that we created also has MySQL PV claim. So basically, WordPress MySQL is using this volume, and the way it's used is written right here. So first of all, in containers, we see the image. It's a Docker Hub image of MySQL version 5.6. So it's using the container port 3306, and it's also using volume mouse, and it's using the persistent volume storage that we created, and it's mounting our persistent volume storage to its default location, which is var lib MySQL, so that anything it creates will actually not be destroyed when the pods are recreated or such. And finally, the environment variables. So as an environment variable, we want a MySQL root password, and the value is actually taken from a secret key reference, and it's a MySQL pass, and the key is password. And finally, we have a WordPress deployment YAML. So it's just like the previous one, we have the same things. We have a service, a persistent volume claim, and a deployment. So let's check the service first of all. Targeting the WordPress frontend, and it's a load balancer so that the external traffic can access the frontend on port 80, of course. And next, we have a persistent volume claim. It's a WordPress PV claim, and it's requesting 20 gigs. Next, we have the deployment. The deployment has the label app WordPress. And just like before, we have containers and volumes. In the volumes, we're using the PVC that we just created. Next, in the containers, we have an image of WordPress from Docker Hub running on version 4.8. It's running on port 80, and we see that it's mounting the persistent volume in the default place where it places its HTML files at var www.html. And last thing to note is the environment. First of all, it's setting the WordPress database host with this value, and it's setting the WordPress database password with a value from the secret key reference. And we can actually add both of these deployment files into the customization YAML. And to do that, you basically add these three lines: resources and dash the first YAML, dash the second YAML. And then you apply the entire customization file with kubectl apply -k and specify the folder where it is. If you type get PVC, you get the MySQL PV claim as well as the WordPress PV claim, and with the status bound. And now when you access the external IP of the load balancer, you get your WordPress site. That's the stateful example. Alright, that should be enough to give you some solid basis in Kubernetes. Thank you for watching, and goodbye.